Thank you. As last speaker of the Focus Week, I'm going to ask you to join me and thank the organizers. All right, so let's continue with the previous discussion. So remember, starting with the manifold, smooth manifold, you can associate this sheaf of vertex algebras, so this kind of the wrong sheaf. Algebras. And this is can be thought of as a quantization of occurrence of t plus t star, which in turn we can think of as sitting inside functions on the potential bundle of the group space. And so this gives us a first approximation to the quantum kinematics of contractible loops propagating in X. Now, if the loops are not contractible, then we saw two examples. One, that of torus, and in that case, again, so there are several ways of quantizing this. One using the Lagrangian approach, one using this Hamiltonian picture, and in that picture, natural thing to do is to pass to a manifold of twice the dimension without the torus, and then we get that we can extend the vertex algebra structure on the vertex algebras of currents of t x plus t star x to a bigger algebra. So this was identified with the tangent bundle to this bigger manifold. So extend this to include the functions on y. And as a consequence, we were able to recover the lattice vertex algebra associated to the tautological lattice that defines this, and this is an extension of chiral to include all y-nets. Now, in slightly more complicated example, we looked at the three-dimensional torus twisted by 3,4H, or equivalently the Mill manifold N, which is the quotient of the two-dimensional Heisenberg group by a lattice. And then we got a more complicated structure on OY denser U current of Y, where now Y was a six-dimensional manifold, again fibered over X with T3 fibers. And so this was the sections of these guys. This was not a vertex algebra, because of value logarithmic singularity. So it looked like a vertex algebra in many other aspects. And then one question was, this diagram seems to suggest a three-dimensional geometry appearing into the picture, which it's not clear how to explain, so this was one question. Another question is, can you find a semi-classical or quasi-vertex algebra limit of this construction? Okay, so this might be a little bit tricky, and let me point out something that may be also one of the reasons why this structure is more complicated than one might expect. So let's look at coordinates here: x1, x2, x3 on the three-dimensional torus, and x1 star, x2 star, x3 star coordinates on the fiber torus. Then h1 of y is spanned by dx1, dx2, dx3, and dx1 star minus x2 dx3, dx2 star minus x1 dx3, and dx3 star minus x1 dx2. So now there is a natural two-form that one can try to write on y by pairing the non-star coordinate with the corresponding star coordinate. So we get the form omega, which is dx1 dx1 star minus x2 dx3 plus dx2 dx2 star minus x1 dx3 plus dx3 dx3 star minus x1 dx2. And as you can check, this is not closed. So there is a natural twisted Poisson structure that lives on y, defined on functions on y, and it's the type of pairing between functions on the fiber and function on the base that does appear in the structure that we constructed here. So maybe this is one of the reasons why the structure is more complicated than normal. But I think finding a semi-classical limit is an interesting question. So this brings me to the next topic that I wanted to talk about, which is that of
so something's not integrable.
Right. So because of the geometry, this equation is non-trivial. If I wrote the same form for the torus, that would give me a perfectly fine symplectic structure, but this is non-integrable. The failure of being integrable is measured up by this pullback. This one. So n equals to 2 supersymmetric objects, so particularly conformal algebras, and Poisson vertex algebras, and so on. So the idea is that everything we worked out for the non-supersymmetric case has a natural extension if one replaces the category of modules over this differential operator, which was thought of as differentiation on the worldsheet space coordinates. If we replace it by a super analog, which we will call sk d plus or minus d, which is k d plus d minus d, where these are put as odd, and the quotient by the relation that even b is given by d plus and minus.
Just one more question. You said it's not integrable, so it's not symplectic, but it is Poisson.
No, I think it's twisted Poisson. So.
Twisted.
So modules over this super differential ring, but the whole construction worked out in the same way. So you have the conformal algebras. Before we had this bracket, now this corresponds to a super bracket that encodes derivatives of the delta function both for even and odd coordinates, and so on. And one can take universal numeric algebras. Everything more or less works out in the same way. So this has a nice application to the study of n equals to 2 structures on parallelogram. So I can start with X, just manifold, and phi, vector field on X, such that all X with phi is a Poisson algebra. And so then I can make this into a module over this super differential ring. So I can just tensor with it. To a free SK module related by OX. And so this, I can make it into a n equals to 2 deconformal algebra in that sense. By imposing the relation that when I take the bracket of 2 functions, then this should be the Poisson bracket of f and g. And doing this, you get the extreme Domenico Seminara sheaf on X that is constructed as the quotient of the universal developing algebra of this object field that we just constructed. Quotiented by the relation that tells us that the product that was part of the Poisson structure product of function should be equated to the normally ordered product in this the universal developing algebra, which is a vertex algebra, and the differential should act by the Leibniz law. By carefully taking into account the normally ordered product. So we get d plus or minus f, g plus normally ordered product of f, d plus or minus g.
So you're doing the non-twisted case now?
Non-twisted.
Well, you said this was twisted over here.
Oh yeah, this is just ordinary post-op. Yes, absolutely.
Non-twisted.
So this is the sheaf.
Twisted would mean the tensor product is not really.
It's the sheaf of n equals to 2 vertex outputs on S. The reason why it's a sheaf is because this was a sheaf and the relations was locally or the manifold, so it's still a sheaf. Alright, so now this is a generalization of Carl because those authors prove that if the Poisson structure is not degenerate, then this sheaf is isomorphic to Carl. So this fact helps. So this gives you something for any Poisson structure, but even in the non-degenerate case, where this is isomorphic to parallelogram, this approach gives you a way to think about n equals to 2 structures on these objects, which is particularly convenient. So you can package the local coordinates, local sections of chiral graph, which are local to the BC beta gamma system, into a single superfield. Capital Phi, and in such a way, all the relations between the variables of the beta gamma system gets encoded very simply in the statement that the lambda bracket of phi mu and phi nu should be given by the Poisson tensor. Which coordinate factor we get. Any question so far? So now, if x is scalar, then we can write local sections of this sheet as can write two local sections, G tilde plus or minus omega alpha beta bar, well, derivative plus or minus of alpha, and one has to be careful about which order we take the product, v minus plus p beta bar. Well, one can justify why one would look at this by rewriting in the Lagrangian formalism as well, by rewriting the action in a suitable way, referring to Maxim's paper for the details. But this is some local section that can be written in using the variable that we introduced. Omega is the symplectic form that is part of the Taylor structure, and it's the inverse of the Poisson. So, it's local sections, and then one can ask whether they glue together to global sections. And it turns out that this is not always the case. So what happens is that under a change of coordinates, where the z coordinates will go to z tilde, what happens is that g plus or minus picks up a factor which is a constant times the derivative, the logarithmic derivative of the determinant of the Jacobian, of this change of variables. So this shows that in general these sections are not well defined, and so we have to correct it somehow. So if x is...
Yeah, do you have some explanation for this? Just to some intuitive explanation for this change?
Well, I'll say something about this, how it relates to another problem. Yeah, I don't know what intuitive is in this case. It's a calculation. You can see that this work happens. I mean, I think the biggest problem maybe is that this is not intuitive in the first place to write down. So, anyway.
So it's invariant under what kinds of transformation?
So change of coordinates on the z is the worksheet. So if x is Calabi-Yau, on the other hand, then we get a global volume form, a homomorphic form. That you can write in this way. Oh, sorry, those are the coordinates on x. Which I write in the z. This is confusing because there's a z for the other coordinates as well. These are the private coordinates. Okay, so then what happens under this coordinate change is that f goes to f minus the derivative of the logarithm of the determinant of a, of course. Just by change the variable form. And therefore, this means that in this case, we can write well-defined sections by writing g plus or minus as taking the old g plus or minus tilde and correcting it by plus or minus square root of -1 times f. That was by f bar. So the change in here cancel out with this extra term that we got here.
Again, this f goes to f minus?
That was the logarithm.
Log.
Okay, so in this case, one can check that these sections, they give you two commuting copies of the n equals to 2 superconformal algebra sitting inside this sheet here. In fact, more generally, if X is just symplectic, without further qualification, we get one copy of n equals 2, because by adding or subtracting g plus and g minus, you can get rid of this factor, so there's no need for correction. While if f is complex with volume form as above, you get also a copy. Okay, of course. All right, so now a remark. So there is a similar.
What do you mean you get also copy? You mean an additional copy or?
No, in this case I just need symplectic, and here I just need complex, but with this condition on volume form, so that so in this case you take one of the combination of g plus and g minus, it will basically get the other combination of g plus and g minus. So it is a similar picture arising in the usual sigma model based on Lagrangian formalism. So perturbatively, so if you start with the Kerr manifold, then classically you see that you have the Lagrangian has these two copies of n equals to 2, the supersymmetry acting, that preserve the Lagrangian. However, perturbatively, you get correction at one loop that is proportional to the first Chern class of X. So, so you can see this by scaling arguments, or more precisely by doing the renormalization calculation. You see that the Kähler form gets changed by constant times C1x. And so we need to impose C1x equal to 0 for everything to work out. So so this first one, this calculation was made. Then people thought that then what we need is to have a Calabi-Yau manifold with the Ricci flat metric. But then it turned out that well, there are also no corrections at 2 and 3 loops, but at 4 loops. So these are Vandenberg and Zenon found a correction to a Ricci flat metric. So
one would think, though, that that correction wouldn't show up in the sort of thing you're doing.
the
I would expect that that correction would not show up in the sort of thing you're doing.
right. So that's the point. So in the construction that I just explained, which is due to Ekstrom and Zabzine, one gets these two copies of n equals to 2 superconformal, commuting copies of n equals to 2 superconformal algebra on the nose, and there is no need for further corrections. If one uses the Ricci flat matrix. However, this seems to suggest a potential mismatch between the usual sigma model picture and this new this Hamiltonian approach. However, one thing to keep in mind is that this correction wasn't the end of the story, because Nemeshansky and Sen showed that, in fact, while one does get perturbation, possibly at all orders, but they all stay within the same class, the homology class of the Kerr class. So, Nemeshansky and Sen showed that from 2 loops on, or 3 loops, 4 loops, and so on. So here there's no correction, but the point is that the argument works for any number of loops. There is, the fact is that omega changes by an exact form. And so it stays within the same homology class, and therefore, well, first of all, anything that just depended on the homology class is still valid. You can compute it in any using any matrix that you like. Also, Yau's theorem, in fact, tells you that not only you can find a Ricci flat matrix, but for any form in the Kerr class, you can find a matrix that solves the Mons-Jumper equation with respect to that form.
But I understand that string exact metric is not a Ricci flat, right?
Well, that's I mean, I don't know, but all I know is this result, which doesn't rule out the fact that it could be Ricci
No,
flat.
it does rule it out, because
Does?
the Ricci flat Keeler metric is unique in its cohomology class.
But this construction is done term by term with the expansion. How do I know that I cannot come back to the original?
Because it's an asymptotic expansion. You have a function that has a non-zero asymptotic expansion. So the function isn't zero. Possibly you're asking if
what is the parameter?
the parameter is
The number of loops?
1 over the volume.
1 over the volume. Okay. So then
If there isn't a parameter, if anyone talks about a loop expansion, there has to be a parameter. Otherwise,
No,
no, talk about loop expansion. And the parameter is 1 over the volume. And my understanding is that the relation of what you're discussing to the standard sigma model is that you're discussing a holomorphic sector, roughly speaking,
right.
which does not see this kind of correction.
No, I don't think, because so what Heloni did, he took a Calabi-Yau, he took a Calabi-Duran complex, and then he proved that if you give him a Ricci flat metric, he can construct 2 commuting copies of super-Virasov with the charge 3 over 2 dimensions of the manifold.
Let's discuss that later.
Okay.
I don't want to interrupt this in our attention.
But yeah, so this is a potential puzzle that maybe can be addressed. From a practical point of view, it's one doesn't know, one cannot write down the Ricci flat metric anyway, so the fact that there is a perturbation to it doesn't affect much.
What's considered to be the main reason this result is important is the following. There's a classical moduli space which is actually a cone, a Kähler cone. And if the classical metrics had been the correct metrics in the string theory, the stringy moduli space would have been the same as the classical one. And therefore, for example, mirror symmetry would have been possible, because on the B model side, the moduli space isn't such a canonical space. So the fact, when the volume is large, the metric is almost the classical one. But when you get inside, it's quite different. But once you have a correction of the classical metric, there's no reason that the moduli space has to be more than asymptotically canonical. So the main qualitative importance is that the sigma model moduli space is only asymptotically canonical. And therefore mirror symmetry is possible. For example. Not only mirror symmetry, but all kinds of stringy effects.
Right. But yeah.
So there are more elementary ones. For example, birational transformations that you can make continuously. That wouldn't happen if each space had its own canonical moduli space. Instead, the two are asymptotically canonical, but inside they can be connected.
All applications that I know for mathematics, they only use the Kerr class. So that for mathematician that is very important that you don't change the Kerr class. But,
it's also important for physicists. The proof that you can correct the metric depends upon the fact that you're not trying to correct the Kerr class. In other words, what the proof goes as follows. You have the Ricci-Flack-Taylor equation, Rij bar equals 0, but it will have quantum corrections. You prove that the quantum corrections are dB bar of something.
That's right. Yeah, so all these
and that
higher proofs involve higher mixed derivatives that are using
so the uniqueness part of the Flavial theorem says that the equation R equals dB bar of something has a unique solution, whatever the solution is.
Right. Perhaps a remark. So more generally, if X is not necessarily Calabi-Yau, but a Hermitian, then you can the right place where dB bar, the logarithm of the metric should live. Is we can define it to be equal to the first Botcher class of X, where the manifold is scalar. This is the same as the Chern class, but more generally this leads in the first Botcher cohomology, which is the intersection. The 1-1 forms, first or second, 1-1 forms that is the kernel of E modulo the image of DC. And for some class of manifolds, one can prove an analog of Gauss theorem that any form here can be realized by the metric which formed the one that you started. So this, I think it would be interesting to look at if for those manifold one can repeat a similar story and see what you get. In particular,
look at this in the context of heterotic organal geometry.
In the context of what?
Heterotic organal geometry.
Yeah, so, but the question is, can you approach this problem using this chiral-around formalism as they did?
The problem is that the solution of Bianchi identity is very sensitive to the choice of connection.
Mm-hmm. Yeah, so it wasn't a statement that this is true. I should have said it as a question. I mean, I think I said it, but I didn't write it up. So maybe one can do this only for some x, not for all of them. But I don't know. I think it's an interesting question because in here it was assumed the manifold to become the autostatic. So there are some weakening where some of the mathematics look similar, so maybe something can be done. But my emphasis here is that I'm not interested in reproducing something like this using the Lagrangian approach, but just the Hamiltonian approach. Okay, so to conclude, let me go back to the examples that I worked out. So, one question. Look for n equals to enhancement of the quantization of the sigma Hamiltonian sigma model on this model that I introduced before, the two-dimensional torus, or dual the manifold n. To get something interesting, probably one wants to cross with a swan, which doesn't spoil the duality or any aspect of the quantization that I introduced. So this, on this side, this is the underlying manifold for the quadrilateral surface. I think it's a complex surface of the quadrilateral Thurston manifold. I think it as a symplectic manifold. You cannot have both. This manifold is not scalar because it has the wrong Bethe numbers, and this also is not scalar for the same reason. But what I find interesting is to study this from the double geometry perspective. Double field theory. So remember, we have this bigger manifold n, while it is pi over x with pi over 3, the double torus. So it's easy calculation to see that if I start, say, with x, and I look at the twisted t plus t star, so I can, classically, I can look at generalized complex structure here, which corresponds to isotropic subbundles and give the right splitting. So generalized complex structure here. And so these they correspond to complex structures on Ty. And well, even just at the classical level, I think this is has been pointed out by many people. But what I think it's interesting because you can have application to the study of global properties of the modular space. Global modular. Because thinking about maybe global modular spaces of generalized complex structure, it's not something that has been studied a lot, but here this was process 1. Process 1 is one dual. This is process 1 dual. So this is process 1 dual. So global property of the modular space of complex structure on a manifold are better understood. There's work on it, and so this can give something interesting for the study of global moduli of generalized complex structure on these objects. But of course, the big question is to find n equals to 2 structures on this mysterious object that I discussed in the previous slide. So even though we don't have a very good axiomatic definition for this object, but still it's written out very completely. So you have the Hilbert space, you have this operator second unit, and you can ask for a copy of the n equals to 2 superconformal algebra, or more than one copy sitting inside this object, and see what it gives rise to. I think I'll stop here. So
any questions? Okay, if there are no questions, let's